Hey there, I'm working my way through the practice physics GRE problems. I've got a gem of a mechanics problem tonight. It's number 59 off of the 2001 practice physics GRE. And as I read it, you'll be laughing, thinking that's not a mechanics problem. It actually is, but it's a little bit of a problem in disguise. So I'm going to go ahead and read it for you. Number 59. For an inductor and capacitor connected in series, the equation describing the motion of charge is L times the second time derivative of Q plus 1 over C times Q equal to 0, where L is the inductance, C is the capacitance, and Q is the charge. An analogous equation can be written for a simple harmonic oscillator with position x, mass m, and spring constant k. Which of the following correctly lists the mechanical analogs of L, C, and Q? Okay, so there's all of my answers. As usual, I want to glance at my answers. Nothing's going to pop out at me at this point as me being able to eliminate any of those options. I need to kind of know what's going on and get something to compare, because this is an analog problem. I need something to compare with that equation that they give me. This is kind of like the SATs. You know, this is to that as what is to that. It's an analog problem. And so I need to get something close to this form of this equation for a spring system in simple harmonic motion. And so I need an equation of motion for something undergoing simple harmonic motion. And the easiest way for me to get there, me personally, you may be able to draw right on the board here the equation of motion for a simple harmonic oscillator immediately. You may remember that immediately, and if you can, that's fantastic. For me and those people that are like me, I want to write these couple extra steps to kind of help you get there if it wasn't immediately obvious. The force acting on a body, the spring, is causing this force on the body, and it obeys Hooke's law because it's a spring. So we know a spring can cause this type of restorative force that you pull it in the x direction and the force is in the negative direction multiplied by some constant. I'm butchering Hooke's law here. I'm sorry, but it's simple. We all know Hooke's law, right? Okay. So anyways, that's the only force acting in that direction on that body. So you're imagining this mass going back and forth in simple harmonic motion. That's the only force that's causing that acceleration of the body. So I can rewrite that as, due to Newton's third, as that's the mass of the body times the acceleration it's undergoing, and that's equal to negative kx. Okay? It's a little crooked there, but you get the idea. So another way to write that is the mass times the second time derivative of x equals to negative kx. And if you remember this type of thing from a mechanics class or whatever, and that's the first thing that pops into your head, and you're sure about that, then fine, you got there with one or two less steps than I did. That's fantastic. You can of course write this another way to even make it look more like the problem, which is great. And I would move this over here because, again, I'm trying to make this look as much as possible as this. That's what I'm doing, so I can compare the two. And so what I'm going to do is I'm going to write this equation in here as well, so it's easy to compare the two. I've got that all right. So there you go. Now you can compare those two. So here, where I have L, up here I see M. I guess I could use an arrow equal sign, maybe some type of arrow, just to show that I'm comparing them. Is what I'm doing. Where I see Q here, I see X up here. Oops. Did that wrong. Q X. Okay, and then where I see, and this is the only problem where it's a little tricky, where I see 1 over C here, I see K there. And another way to say that is where I see C here, I see 1 over K there. In other words, if 1 over C equals to K, of course I can just manipulate that algebraically and I get, C equals 1 over K. It's the same thing. So I can go ahead and erase this one. As long as you understand how I made that jump, that's all right. So there I have it. I have L, C, and Q, and they're analogs in this situation. And so from there, I can pick out my answer pretty quick. And as it turns out, it's let's see, where I see L, I see M. Okay, so it's either A or B, right? Where I see C, I see 1 over K. So right there, I've got to choose B. And then I check the last part anyways. Where I see Q, it's X. Okay, so answer B is the one that I want. Turns out to be the correct answer. I would pick it and go on with things. So that's a great problem. It's a very easy problem, I think. The only reason it's difficult is because it's a mechanics problem disguised as a circuits problem. So I guess the take-home message in a problem like this is that you should realize that there are problems on the physics GRE that are disguised. And so they're going to look like something else to try and trip you up. So don't fall for it. Read the problem. See you next time.